India's first 28-nanometer chip factory just shook the tech world. Some moments in industrial history are only understood in retrospect. The first steel mill that opened in a country that had always imported steel. The first automobile assembled on a domestic production line in a nation that had always bought cars from abroad. The first commercial airliner rolled out of a hangar in a country whose engineers had once been told that the complexity of aerospace manufacturing belonged to someone else. In each case, the moment itself was visible, but the full weight of what it meant, the supply chains that would form around it, the capabilities that would compound from it, the strategic independence that would flow from it over decades, that weight was only measurable in hindsight. India's first 28-nanometer semiconductor fabrication plant is one of those moments. The chip that will come off this line is not the most advanced chip in the world. The leading edge of semiconductor manufacturing, the 3-nanometer and 2-nanometer nodes, being produced at TSMC in Taiwan and Samsung in South Korea, is a different category of technological achievement. India's industry analysts and technology press knows this. The global technology press knows this, and the engineers who built this facility know it better than anyone else. But they also know something that the commentary focused on process node comparisons misses entirely. The gap between having no domestic semiconductor fabrication capability and having a 28-nanometer domestic semiconductor fabrication capability is the largest gap in the entire spectrum. The gap between 28 nanometers and 7 nanometers is real, but bridgeable. The gap between 0 and 28 nanometers required crossing a threshold that the world's most advanced economies spent decades and hundreds of billions of dollars to cross. India crossed it. And everything that follows from that crossing will compound in ways that make the first chip the least interesting thing that will ever come out of this factory. Let us understand what was actually built and why building it was harder than anything the headline numbers suggest. A semiconductor fabrication plant, a fab, is not a factory in any conventional sense of the word. It is the most complex manufacturing environment that human civilization has constructed. The clean room at the heart of a semiconductor fab maintains air purity levels that make a hospital operating theater look like a construction site. Class 1 clean rooms, the classification that leading-edge fabs require, allow fewer than one particle larger than half a micron per cubic foot of air. For comparison, ambient outdoor air contains millions of such particles per cubic foot. A single dust particle landing on a wafer during processing destroys every circuit it touches. The photolithography systems that print circuit patterns onto silicon wafers use light of wavelengths shorter than the features they are creating, requiring optical systems of almost incomprehensible precision. The chemicals used in semiconductor processing are some of the purest substances manufactured at industrial scale. The water used in semiconductor processing must be purified to a degree that makes pharmaceutical-grade water look like tap water. The vibration isolation systems that protect sensitive equipment must suppress disturbances measured in nanometers from sources as remote as passing trucks. The temperature control across the fab floor must be maintained to fractions of a degree. Building this environment is hard. Staffing it with engineers who know how to operate it is harder. Maintaining the yield of working chips at economically viable rates from the equipment running in it is harder still. The yield problem is perhaps the least visible and most important challenge in semiconductor manufacturing. A new fab does not immediately produce chips at the same yield rates as a mature fab. The process has thousands of steps. Each step has hundreds of variables. Getting all of those variables into the right ranges simultaneously, consistently, takes months to years of production ramp. During that ramp, significant fractions of the wafers processed produce chips that fail quality testing. The cost of those failures is borne while the fab's revenue is limited. The capital cost of the facility is being serviced. The engineers are being paid. The chemicals and gases are being consumed, and the output that passes quality gates is a fraction of what the fab will eventually produce. Surviving the ramp while maintaining the financial discipline and the engineering focus required to drive yield from unacceptable to competitive is the test that separates successful semiconductor manufacturers from expensive failures. India has entered this test. The outcome will depend on execution over the next 2 to 3 years, but the fact that India has entered it with a facility that has the equipment, the clean room, the process technology license, and the engineering workforce to attempt the ramp is itself the achievement. Because getting to the starting line of this test required solving problems that India had never solved before. The facility that achieved this milestone sits in Dholera, Gujarat, part of the Dholera Special Investment Region, one of the most ambitious planned industrial development projects in modern Indian history. The location was not accidental. Dholera was chosen for its land availability, its planned infrastructure connectivity, its access to the water supply that semiconductor fabs consume in enormous quantities, and its inclusion in the industrial corridor that connects it to port infrastructure necessary for the import of process chemicals and equipment and the export of finished product. The anchor investor in the facility is Tata Electronics, the same company that demonstrated world-class manufacturing quality through its role in Apple's iPhone supply chain. Tata's partnership with PSMC, the Taiwanese semiconductor manufacturer, brought process technology, equipment specifications, and the production knowledge that makes the difference between a building of expensive equipment and a functioning semiconductor fabrication operation. Process technology transfer of this kind is not simply documentation, it is people. Engineers from the technology partner working alongside Indian engineers, running processes, diagnosing problems, training the judgment that cannot be written in a manual. The engineering workforce that is ramping up in Dholera is learning from people who have run these processes before. That knowledge transfer is the most valuable thing the partnership provides, and it is being absorbed by Indian engineers who will carry it into every subsequent generation of Indian semiconductor development. The 28-nanometer process node that this facility will master is not the frontier of what is possible in semiconductor manufacturing, but it is the frontier of what a very large fraction of the world's actual chip demand requires. This is a point that gets missed in discussions dominated by the leading edge. The most advanced chips, the 3-nanometer and 2-nanometer processors in the latest smartphones and AI accelerators, represent a small fraction of the total semiconductor units consumed globally. The vast majority of chips in the world are not leading edge. They are mature node chips running at 28 nanometers, at 40 nanometers, at 65 nanometers. The microcontrollers in automotives, the power management chips in consumer electronics, the connectivity chips in IoT devices, the display driver chips in every screen, the radar chips in driver assistance systems, the industrial control chips in manufacturing equipment. India's domestic electronics industry consumes enormous quantities of these chips. Every smartphone assembled in India, every television manufactured in India, every automotive built in India, every industrial control system deployed in India, all of them contain chips that a 28-nanometer fab can produce. The domestic demand for exactly what Dholera will produce is larger and growing faster than the facility's initial capacity can serve. This means the fab does not need to compete for export market share on day one. It can ramp its production, learn its process, build its yield, while selling into a captive domestic market hungry for domestic supply. That market structure is unusually favorable for a new entrant. Most new semiconductor fabs face the brutal challenge of competing for customers against established manufacturers with lower costs, proven processes, and existing relationships. India's fab faces a domestic market that has policy incentives to buy Indian chips, strategic motivations to reduce import dependency, and commercial demand that exceeds what the facility will initially produce. The ramp economics are meaningfully better than they would be for a comparable facility trying to capture market share in the open global market from a standing start. And the strategic motivation is even more compelling than the commercial one.
India's semiconductor import bill runs to tens of billions of dollars annually. Every chip India buys from Taiwan, from South Korea, from China represents money leaving the economy, and more importantly, a dependency on supply chains that the world has learned can be disrupted. The COVID pandemic exposed the vulnerability of concentrated semiconductor supply chains in a way that permanently changed how governments think about this dependency. Automobile factories idled for lack of chips costing a few dollars each. Consumer electronics production disrupted for months. Medical device manufacturing constrained at exactly the moment when medical devices were most needed. India watched this happen while it was happening to everyone. And India's policymakers drew the same conclusion that American, European, and Japanese policymakers drew. Semiconductor supply chains that run through a small number of concentrated facilities in geographically and geopolitically exposed locations are a national security risk as much as they are an economic vulnerability. The CHIPS Act in the United States committed $52 billion to domestic semiconductor manufacturing. The European CHIPS Act committed over 40 billion euros. Japan committed billions to attract TSMC to build domestic fabrication capacity. India's Semiconductor Incentive Program committed $10 billion to attract and support domestic fab investment. The Dholera facility is the first major result of that commitment. It will not be the last. The signal that a functioning 28-nanometer fab sends to the global semiconductor ecosystem is that India's commitment is real, and that the ecosystem investment it attracts will compound. The supply chain that forms around a semiconductor fab is as economically significant as the fab itself. Specialty gas suppliers, chemical suppliers, equipment maintenance providers, substrate suppliers, packaging and testing facilities. The entire ecosystem of specialized suppliers that a functioning fab requires creates an industrial cluster whose total employment and economic output exceeds the fab's own direct contribution many times over. That cluster is beginning to form around Dholera, and as it forms, it reduces the cost and complexity of operating the fab, and reduces the cost and complexity of building the next one. The Micron Technology Facility, also under construction in Sanand, Gujarat, is building semiconductor assembly, testing, and packaging capability that complements the fabrication capability at Dholera. Together, these two facilities begin to create an end-to-end semiconductor manufacturing presence that India has never had. Raw wafers in, tested, packaged chips out. The full manufacturing value chain on Indian soil under Indian governance. The defense implications are as significant as the commercial ones. India's most advanced military systems, its radar systems, its missile guidance computers, its electronic warfare equipment, its communication systems, all require chips. Currently, those chips are either imported or, in the most sensitive applications, sourced through supply chains that involve foreign technology that comes with end-user restrictions, foreign visibility into what India is building, and foreign leverage over India's military capability development. A domestic semiconductor manufacturing capability changes this equation. Not immediately, not for the most advanced applications that require leading-edge chips, but for the large category of defense electronics that runs on mature process nodes, on 28-nanometer and similar chips, domestic supply becomes achievable in a time frame that defense planners can incorporate into their programs. The ability to design and manufacture chips for sensitive military applications without foreign visibility into the design or foreign control over the supply
is a strategic capability with implications that extend far beyond the economic value of the chips themselves. The education system that must scale alongside this industrial development is already responding to the signal that Dholera sends. Semiconductor engineering programs at IITs and NITs that were producing graduates who predominantly joined foreign semiconductor companies are beginning to see a different career path open for their students. Domestic jobs in India, doing the same work that previously required emigration. The brain drain that has cost India some of its best semiconductor talent for decades begins to reverse when the domestic opportunities match what is available abroad. Not fully, not immediately. The salaries at leading global semiconductor companies will remain competitive for years. But the pull of working in India on India's program, building India's capability, is a pull that many engineers feel and will now be able to act on. The global technology reaction to India's first 28-nanometer fab has followed the pattern that India's technology achievements have increasingly produced. Initial skepticism giving way to verification, giving way to recalibration. The skepticism was understandable. India has announced semiconductor ambitions before that did not materialize. The history of semiconductor fab announcements that became lengthy delays or quiet cancellations gave legitimate grounds for caution. This time is different because the facility is real, the equipment is installed, the clean room is operational, the process development is underway, the first wafers are being processed. The skepticism that was warranted before the facility was built is not warranted now that it exists. And the recalibration that follows verified reality is the recalibration that matters, because it changes what India is offered next. The technology partners who would not transfer process technology to India before it had demonstrated capability will consider transfers now. The equipment suppliers who serviced Indian customers as a secondary priority will see India differently when India is a functioning fab customer rather than a potential one. The engineers and researchers who chose careers in Taiwan or South Korea or the United States because the domestic opportunity was not real will look again. And the next fab, which is already in planning stages at multiple sites, will be easier to build, faster to ramp, and more capable in its target process node than this first one, because the first one did the hardest thing. It started. The chip that rolls off this line, tested, packaged, and ready for installation in an Indian automobile, or an Indian smartphone, or an Indian defense system, is not just a semiconductor component, it is proof. Proof that India can do this, that the clean room can be built, that the process can be run, that the engineers are here, that the capability is real. Every proof of this kind that India has produced in the last decade, the lunar landing, the AI supercomputer, the jet engine, the deep-sea vehicle, the quantum mission, has been followed by the next achievement arriving faster than the previous one, because capability compounds. The first chip is the least impressive thing India will ever make in this facility, and the world, still recalibrating from the shock of seeing it exist at all, is beginning to understand what that means. India has entered the room where the world's most critical technology is made. The door is open, and India is not going to close it behind itself. It is going to build a bigger room.